Okay guys, today we're going to continue with systems of equations, and today we're going to be looking at a method called elimination. So with this first example, we're going to solve the following system by substitution, and in this case there are no variables without coefficients, but we can still solve for one of the variables. It just means that we're going to get fractions. So let's solve for x in equation 1. So in equation 1, 3x equals 19 minus 2y. And then we'll divide each thing on the other side by 3. So that's what it's going to look like when we solve for x. We'll call that equation 3. And now we're going to sub equation 3 into the other equation we haven't used yet, which is equation 2. So I'm going to put 19 over 3 minus 2y over 3. It's going in place of the x. And then we have minus 2y equals 5. So at this point we need to multiply the 5 inside the bracket here to clear the bracket. So 5 times 19 is going to give me 95 over 3 minus 10y over 3. And then we just have the minus 2y equals 5. So at this point, when we're solving equations and we have fractions involved, we can multiply each term by a factor that will get rid of the fractions. So in this case, we only have 3's as our denominator. So if I multiply each term by 3, that'll clear the fraction and it doesn't change the equation in any way. So here, these 3's divide each other out. So I'm left with just 95 there. These two 3's divide each other out. So I'm just left with minus 10y there. And then 3 times 2y is going to give me 6y. And 3 times 5 is going to give me 15. So that's what it looks like when we clear the fraction. Then we isolate the y. So I'm going to move the 95 to the other side. I'm going to have minus 16y equals minus 80. And if I divide by negative 16, I get y equals 5. And hopefully remembering from yesterday, once we get y equals 5, we still need to figure out what x is equal to. So I'm going to sub y equals 5, and I'm going to substitute it into equation 1. So in equation 1, I've got 3x plus 2 times y, so that's going to be 2 times 5, equals 19. So 3x equals 19 minus 10 when we take the 10 to the other side. X is going to equal 9 divided by 3, so x equals 3. So therefore, our point of intersection is 3, 5. So that's our solution for that one. A little bit messy with the fractions when we were substituting in at the beginning, but interesting that we just got nice whole number answers at the end. So here's where I want to show you our different methods. So one of the things that we know is that we can add, subtract, multiply, and divide by anything on both sides of an equation, and we still have an equal expression. Now that we're working with systems of equations, I want to show you something. So if I write an equation here without x's and y's, just a true equation, so 3 plus 1 equals 4, and I write something like negative 5 plus 10 equals 5, those are true equations, and number them 1 and 2. Now if I was going to take equation 1 and add it to equation 2, so I'm going to just add each column here. So 3 plus negative 5 is negative 2. 10 plus 1 is 11, and 5 plus 4 is 9. Notice the equation we get at the end is negative 2 plus 11 equals 9 is also a true equation compared to the ones up above, and they're also true as well. So what happens if I subtract? So if I have 3 plus 1 equals 4, and I've got negative 5 plus 10 equals 5. So this time, if I subtract these equations, so if I take the terms in equation 1 and subtract the terms in equation 2 that they line up with, so it's going to be 3 subtract negative 5, it's going to be 3 plus 5. 1 subtract 10 is going to be minus 9. And 4 subtract 5 is going to be minus 1. And once again, we see that if we subtract the equations, we get a true answer as well. And the reason we do that is because we can use that technique when we have a situation like this. So you can see here I've got two equations. All of the variables have a coefficient in front of them. So what I can do here is, if you notice, these coefficients match up with each other. And I'm more concerned about the number than the sign. But when they match up like that, I can add or subtract these equations together to eliminate one of the variables. So if I add 2 and negative 2, that's going to give me 0. So I'm going to add these two equations and watch what happens. 3x plus 5x is 8x. 2y plus negative 2y is 0. And 19 plus 5 is 24. So I solve that equation, 24 divided by 8, and I get x equals 3. And once I get here, then I can sub x equals 3 into either equation. At the beginning there, I'm going to sub it into 1. So 3 times 3 plus 2y equals 19. I'll take the 3 times 3 is going to be 9. Take that to the other side and subtract it. So y equals 10 divided by 2. Y equals 5. So therefore, the point of intersection is 3, 5. If you look back and compare how much work we did in that same question at the beginning to find 3, 5, compared to what we did here, this is a lot less work involved when we use elimination instead of substitution when we've got coefficients in front of the variables. All right? So let's take a look at the next example here. So the key to solving elimination, you need one of the variables to have the same coefficient in each equation. Don't worry about the sign, but the number part has to be the same. So here we actually have the same number in front of the x's and the same number in front of the y's. So we can eliminate either one of these variables. I'm going to eliminate the y's, and the y's are easier to eliminate because if I have a plus y and a minus y, if I add those two equations, then that's going to get rid of the y. Just fix that issue. Just want to make sure I've got enough room here. So I'm going to write 1 plus 2 over here. So when I add these equations together, 1x plus 1x is 2x. Y plus negative y is 0. And 1 plus 3 is 4. So x is equal to 2. And then we sub x equals 2 into, and we've got options there. I'm going to plug it into equation 1. So I'm going to plug it into equation 1. I'm going to have 2 plus y equals 1. Y equals 1, subtract 2. Y equals -1. So therefore, point of intersection is 2, -1. And if I come over to these two equations, here I've got an x and an x. So the only way that I'm going to eliminate the x's there is by doing equation 1 subtract equation 2. Because if I do 1x subtract 1x, then I have no x's. 5y minus 3y is going to be 2y. And 1 minus 3, so 1 subtract 3 is going to be -2. So we isolate the y here, so -2 divided by 2, so y equals -1. And then we're going to sub y equals -1. And we're going to plug that into equation 2. Okay, now it's going to look like x plus 3 times -1 equals 3. So x minus 3 equals 3. X equals 3 plus 3. That's going to be 6. So therefore, EOI is x comes first, so it's going to be 6, -1 for that one. Okay, we're doing well here, hang in. So example 2. In this case, we don't have coefficients that match. But what we can do is, I can multiply an equation by anything I want and to match up the coefficients. So if I take equation 1 times 3, that's going to give me 6x plus 15y equals, and -14 times 3 is going to be -42. So I'm going to call that equation 3.
Tony McMahon, you have a call on line 1. Tony McMahon, line 1.
So in this case, we want to subtract these two equations, because 6x minus 6x eliminates the x's. 15 minus 2y is 13y, and minus 42 subtract 6 is going to be minus 48. So here we end up with a y value of -48 over 13, which isn't really a nice number to work with, but it's what we've got. So now we need to sub y equals -48 over 13 into, and I'll use equation 1. So 2x plus 5 times -48 over 13 equals -14. So 2x, and then 5 times -48 is going to be -240. That's going to be -240 over 13. And then I really don't want that fraction around, so I'm going to multiply each term by 13 to help get rid of that fraction there. So we get rid of the 13s here, and then I have 26x minus 240 equals, and -14 times 13, that's going to be 182, so -182. So 26x equals -182 plus 240, 40 and 18. It's going to be 58. So x equals 58 over 26. And actually, they can both divide by 2, so we end up with 29 over 13. So therefore, our point of intersection is 29 over 13 and negative 48 over 13. All right. Last example. So sometimes we can't just multiply one equation by a number to make the coefficients match up. We have to multiply both equations by a number to get them to match up. So in this case, if I take equation 1 and I multiply it by 2, it's going to give me 4a plus 6b equals 22, and I'll call that equation 3. And if I take equation 2 and I multiply that by 3, I get 9a minus 6b equals negative 48. So that's equation 4. So now you can see that I've got the 6 and the minus 6 matched up here. So if I take equation 3 and I add equation 4, so 6b minus 6b, then that's going to be equal to 0. So what I'll end up with is 13a equals minus 26. A equals minus 26 divided by 13. So a is equal to negative 2. We'll sub a equals negative 2, and we'll substitute that into equation 1. So 2 times negative 2 plus 3b equals 11. 3b equals 11. It's going to be minus 4. It'll move to the other side. It's going to be plus 4. So b is going to equal 15 divided by 3. So we get b equals 5. And when we write the point of intersection,
Ms. Courier,
and it's
we
not...
have a call on line 2. Ms. Courier, line 2.
If we have a point of intersection and it's not x and y, then the variables that they give us we put in alphabetical order. So it's going to be a first and then b second. So that's our point of intersection. And just to note at the bottom of the page there, it says once you have the same number in front of the variable, if they have signs that are, so if the signs are the same, then you subtract the two equations. If the signs are different, then you're going to add the two equations. So we'll practice this tomorrow. And we'll also work on this Thursday in class as well. Thanks. Bye-bye.